what I gave you. What I said was we've got what's called a two-level system. So two energy levels, degeneracies G1 and G2, separated by an amount of energy delta E. And what I've given you there are, first of all, the expression for the partition function. And remember, the partition function is equal to sigma I gi e to the minus ei over kt, where this is the energy relative to the 0 point. There's the 0 point. And so the partition function here is very straightforward. It's simply equal to the sum over the two states, G1 with an energy 0 in there, plus G2 e to the minus delta E over kt. And then what you can do is just go through the algebra of going from the partition function to the energy. You've got to take the derivative of the logarithm of the partition function, and then taking the derivative of that again to get the heat capacity. But this is such a simple and a good demonstration of what's going on that, so those are the expressions up there. It's worth just looking at it and trying to understand what's going on. So just let's work out the fraction of molecules, that are in the excited state. And that's going to be given by G2 e to the minus delta E over kt divided by G1, the partition function, G1 e to the minus delta E over kt, like that. And then the energy of the system is simply going to be equal to this ratio here multiplied by the Avogadro number to give us, to convert it to molar units, and then multiplied by delta E. That's going to give us the energy. So that's, just multiply this thing by delta E, and we get that thing there. And we can rearrange that just by multiplying through by e to the delta E over kt, and we just get G2 times delta E times n Avogadro divided by G1 e to the delta E over kt plus G2, exactly the expression that we've got up there, without going through the formality of sorting out what's going on. So it's simply, what we're doing here is we're simply looking at the number of molecules that are up here and multiplying that energy, that number by the energy delta E. But now let's think about what goes on as you increase the temperature. So just let's go to t equals, let's allow t to tend to 0. What's going to happen then? Well, this term here is going to become infinity because of the 1 over t term, and so the energy then, U, is going to be equal to 0. All the molecules are sitting down in the lowest level. They just don't have enough thermal energy to access the higher state. What's going to happen at very high temperatures, so as T tends to infinity, then this term is going to tend to unity, and we'll just get the energy now will just be Na times delta E times, that goes to unity. We've just got G2 over G1 plus G2. What this means now is that the molecules are populating these levels simply according to the number of states that are there. If G1 and G2 were unity, then we'd have as many molecules up here as we have down there. The populations would be equal. But with the degeneracies there, then those populations will simply be those relative populations will simply be in the ratio of the degeneracy. And so what that means is that if we plot the energy versus temperature, it's going to look something like this. It's going to start off at 0. It's going to go to this expression here. Let's call that u infinity. So it goes to this limit u infinity. And somewhere in the region here is where delta E is of the order of kT. In other words, when this term here is beginning to change significantly. So that's what the energy looks like. And we can also now just draw a diagram of what the heat capacity will look like, because the heat capacity is simply the derivative of this with respect to temperature. So CV, is simply du by dt at constant V. And so if we take the gradient of this thing here, then the heat capacity will look something like that. So that's the contribution from this electronic motion to the heat capacity of the system. It rises at the point where the system is absorbing energy, but then it tends to 0 when the system becomes saturated. So we've put as much energy into the system as we're able to do, because we've saturated the system. We've got the number of molecules are distributed simply according to the degeneracies. And if you play around with this expression up here, you can see that's exactly what it will look like. Okay, any questions on that? Is that okay? And you all derive those expressions up there, I'm sure. Okay, it struck me when I'd done this, I was thinking about it last night and thinking about some of the comments from one of you yesterday, that it might be worthwhile saying a little bit more than I've done so far about heat capacities and energies associated with different forms of motion. Because it's an important, we need to understand energies and we need to understand heat capacities if we're going to predict what enthalpy changes in a combustion system are going to be as a function of temperature. We need those heat capacities. Okay, so let's fairly quickly just go through this on the board. And it's useful to go back to this slide here, which was slide 30. I'm afraid they're not numbered in the things you've got. So this was from the stuff we had yesterday. And this gives you the partition functions. So let's just have a look at those and see what we can find out. And to do this, we need to remember, first of all, that the internal energy is equal to Na. This is Avogadro's number times kT squared times d log q by dt at constant V, and that CV is equal to du by dt at constant V. So let's have a look at those for the various forms of motion. And if we start off with translation, then Q is equal to, just let's rewrite it slightly, 2 pi m k over h squared all to the power 3 over 2 multiplied by t to the 3 over 2. Okay? And if we take d log q by dt, then what we have to do is just to differentiate this and divide it by itself. There's a constant term there, which will occur both top and bottom. And so this is simply going to be equal to 3 over 2 times t divided by t squared. So it's going to be equal to 3 over 2 times 1 over t. So what's the internal energy going to be? U is going to be n Avogadro times kT squared times this. So it's going to be n Avogadro 3 over 2 times n Avogadro times k multiplied by, there's a 1 over t there, a t squared there, so we've got t. So this leads to a result which you all know, which that the translational energy is simply equal to 3RT over 2. And that comes quite naturally out of the partition function. And the heat capacity is going to be the derivative of that, and so CV associated with translation is going to be 3R over 2. And we said yesterday that basically translational motion is behaving classically. If we look at rotation, and just let's do this for a diatomic molecule to make life easy for ourselves, then Q is equal to K over sigma HBC times T. And so we differentiate that, divide it by itself, and we get then that simply that U is equal to R times T, and CV is equal to R. Again, results that you know. One proviso here, and that is that this only really applies at higher temperatures where the spacings of the energy levels are small compared with KT. So we ought to say here we need to beware low temperatures. But those low temperatures are very low temperatures. And so they're not really a concern as far as combustion is concerned. Okay, now vibration's a little bit more complicated because the energy level spacing is now larger than KT, except when we go to high temperatures. And so now we have to work a little bit harder, and I'll get my notes so I don't get this wrong. So Q, again, we'll just do this for a diatomic molecule. So this is vibration, again for a diatomic. Can you read this okay? Is it clear? So Q is equal to 1 minus e to the minus hc omega over kt to the minus 1. So life becomes slightly more complicated now. Let's say that the energy is going to be equal to Na times kT squared. Then we've got to differentiate this thing here. And we are going to get, first of all, taking the term inside this exponential, we'll get hc omega over kT squared. And we're going to be multiplying that by e to the minus hc omega over kT. And we'll then get the square of this term, but we'll get that term itself. So we'll get 1 minus e to the minus hc over kt to the minus 2. And there are various minus signs floating around here, but they all cancel out in the end. So we'll get that to the minus 2, but we'll get it again to the minus 1 when we divide by the quantity itself to get the differential of the log. And so the net result of all of this is that we finish up with, on the bottom line, 1 minus e to the minus hc omega over kt. And we can rearrange that, and we'll get simply r times, there's kt squareds will cancel out, so we'll get hc omega. Let's multiply top and bottom by e to the hc omega over kt, and so we'll get 1 there, and in the bottom we'll simply get e to the hc omega over kt to the minus 1. Okay, are you following this diligently and making sure that I'm getting this right? Okay, so what does that look like? What we've got to do is consider this quantity, hc omega over k, and compare that with the temperature. And this thing is called the characteristic temperature. Of the vibration. So compare that with temperature. So just let's see what's going to happen when the temperature is very low. So once again, this term is going to go to infinity, and the energy is going to be equal to 0. So for T tending to 0, then the internal energy also tends to 0. What happens when we go to very high temperatures? We've got to be a little cleverer here. So we've got the internal energy is equal to R times hc omega. This term here is becoming very small as the temperature increases. And so let's expand it. And we'll get 1 plus hc omega over kt minus 1. Yeah, I've made a mistake here. What I did was I should have cancelled these two terms out, but I absorbed the k into the Na and got R. So that should really be Na times hc omega. And that again there should be Na times hc omega. Okay? So looking at that then, the ones go out and we get simply N Avogadro times hc omega over hc omega times kt. And so these are going to cancel out, and we'll simply get R times T. And so at high temperatures, the vibrational energy tends towards RT, which is the classical limit for vibration. And obviously, the heat capacity is going to be equal to R. So at high temperatures, everything is fine and dandy, but at intermediate temperatures, you've got to worry about the vibrations, and you've got to worry about this quantity here, the characteristic temperature. So if we look at nitrogen, say, the nitrogen molecule, then omega is equal to 2,359 reciprocal centimeters. And so the characteristic temperature is going to be, this quantity here, Hc over K, is equal to 0.659 centimeters. And so if we take that, multiply it by omega, we get a characteristic temperature of 1550 K. And so what this means is that at low temperatures, the vibrational heat capacity of nitrogen is going to be very low, close to zero. As we go up in temperature, it's going to rise, and it's rising in temperatures of the order of 1,000 K, 1,500 K, 2,000 K, combustion temperatures. So the heat capacity of nitrogen is changing with temperature over the range in which we're interested. And on Thursday, I think it will be, we'll do a problem looking at that and looking at the heat capacity of nitrogen and basically using these results. Okay, well, that was quite a digression, but I hope it helps you understand heat capacities perhaps better than some of you did at any rate before, and I hope it answers the question that I discussed with somebody yesterday. Okay, does anybody have any questions on that?
Professor, this high temperature vibrational modes of energy, does it have any bearing on the partition theorem of energy?
On the, yeah. The partition theorem says that basically energy is partitioned equally according to the numbers of degrees of freedom. So for translation, you have 3 degrees of freedom, so you have 3R over 2. For rotation, for a diatomic molecule, you have 2 degrees of rotational freedom, so you have R. For vibration, vibration is slightly different because we have what are called 2 squared terms. We've got a potential energy term and a kinetic energy term. And so the equipartition value for vibration for a single mode of vibration is R. Okay? So what this is saying is that at high temperatures, equipartition works fully, but in between it doesn't, and you've got less energy in vibration than you would otherwise expect from that theorem. Does that answer your question? Any more queries, comments, complaints? Okay. Right. At the end yesterday, we rather skipped through our discussion of branched chain reactions. So just let's go through that again. Okay. So what we said was that if we go to branched chain reactions, then in addition, we talked about linear chain reactions like the hydrogen-bromine reaction, where we said we have initiation, propagation, and termination. In the case of branched chain reactions, in addition, we have branching steps, where one radical produces 2. One chain carrier produces 2 chain carriers. And it's a fairly complicated problem, But what we did was to really make it very, very simple and look at the numbers of chain carriers that are there and at their variation with time. So we looked at dn by dt, where n is the number of chain centers. And we said that that's going to be given by a rate of initiation which is constant. And I'll justify that in a minute. Constant and equal to I. And then a rate of chain branching that depends upon the first power of the chain centers. So here we've got H reacting with O2. O2 is constant, and so this is going to be what we call a pseudo first order reaction. I'll explain that again later on. And then we assumed that we have linear termination that just depends upon the first power of the chain center concentrations. And again, that's going to be a good approximation. And so we solve this, and we get this term down here, I over phi multiplied by the exponential of phi t minus 1, where phi is the difference between the rate constants for branching and the rate constant for termination. And what we did then was to look at what's going to happen if G minus F is slightly positive or slightly negative. And so what's going to happen is we're going to have in here a term which is an exponential of a minus phi is negative, varying with time, or phi is positive, varying with time. And so what I did was to make G minus F equal to minus 1 here. So we have a term e to the minus t. And so what's going to happen now is that e to the minus t is going to tend to 0. And as it does so, n simply becomes equal to I over phi. So to go back, we've got this term here, e to the minus phi t going to 0. It's over a negative phi here, so we've got minus 1 over phi times I. And so what's going to happen then is that n over I increases and then reaches a steady state here, which is equal to I over phi. And phi is equal to 1. On the other hand, if we make G minus F positive, make it plus 1, then what's going to happen is this term is going to increase with time, and the reaction is going to take off. We're going to get ignition. So branching is faster than termination. The number of radicals rises exponentially. Okay, now let's apply that to the hydrogen-oxygen explosion limits. So the explosion limits look like this. Inside this region, we have explosion. Outside it, we have slow reaction. And there are 3 limits. So let's then relate this. So this is pressure going up there, temperature going along there. Let's relate this to what's happening. So this is a slightly extended mechanism from the one I showed at the beginning of yesterday. So this is the initiation process, H2 plus O2 reacting to produce H and HO2. And HO2 at low temperatures is a pretty unreactive radical. And so this, as we move into ignition, before we have ignition, then the concentrations of hydrogen and oxygen are hardly changing at all. And so the rate of this reaction is going to be constant, and we set it equal to I. There's another initiation reaction down here, which won't be constant. And so it depends upon how important it is, just how valid our analysis was. And this is HO2 reacting with H2 to form H plus hydrogen peroxide. And the important thing here is that we've got this slowly reacting radical being replaced by a rapidly reacting radical. We have propagation step, branching steps, and then termination steps, H plus O2 plus M forming HO2, reactive radical being replaced by an unreactive radical, and then H, O, and OH going to the wall. So they're at low pressures, they can diffuse to the wall, and they're deactivated at the wall. And then this other termination reaction here, 2 HO2s going to hydrogen peroxide, but then this important new initiation reaction, which is actually a branching reaction, hydrogen peroxide falling apart to form 2 OHs. So that's the mechanism. And so let's have a look, first of all, below the first explosion limit. And there's no explosion. And what's happening is it's low pressure, the radicals are diffusing to the wall, and termination is faster than branching. When we go above the limit into this peninsula here, then what happens is these propagation and branching steps are now occurring more rapidly than termination. And we wrote these down. We said there's a branching step, H plus O2 going to OH, and that OH will react with H2 to form H in a propagation step. O will react with H2 to form H plus OH, and the OH again will react with H2 to form H plus water. And you add those up, and you get H reacting with O2, this first reaction here, plus 3 H2s going to 3 hydrogens. And so you can look at what's happening there. Each of those hydrogens is producing 3 new hydrogens, and we're moving to a rapid increase in the number of chain centers, and we're getting explosion. We now move into this slow reaction phase here, and now the termination step is H plus O2 plus M, forming HO2 plus M. And that's now occurring more rapidly than the branching steps. So we get no explosion. And then finally, in this third limit, we get these 2 new initiation reactions, HO2 reacting with H2, forming H plus hydrogen peroxide, HO2 generating hydrogen peroxide, and hydrogen peroxide falling apart. And the important thing now is that this hydrogen peroxide dissociation reaction, and we're moving, notice that we have to be at higher temperatures here compared with this explosion, this peninsula down here. The hydrogen peroxide is dissociating, and it dissociates, as we'll see later on today, it's at the third order limit. So as we increase the pressure, then hydrogen peroxide dissociates more rapidly, linearly with the pressure. And so then what's going to happen is this hydrogen dissociation reaction is going to win. So that's a slightly different aspect to it. Now, this is a paper by Professor Law from 2013 in the Journal of Chemical Physics. And it's a very nice analysis of the limits of these reactions using the sorts of ideas that we were developing yesterday when we were using those matrix methods. So he's using those matrix methods here to understand analytically what these explosion peninsulas look like. And here's a more recent paper from Professor Law in Physical Chemistry, Chemical Physics. So the star indicates that that's not in your notes, but it will be in the final stuff that goes on the web. But if you want to look at Phys Chem Chem Phys 2018, volume 20, page 742, and that takes these ideas further and is a very powerful analysis of these explosion limits. And it's a very nice demonstration of some of the ideas we were talking about yesterday, but taking them much further with a lot of insight into just what's going on. Okay, so that's the end of topic 1. So let's move on now to topic 2. Before we get started on that, just let me hand out the homework for tonight. I know how disappointed you'll be if you don't get some. Thanks. Don't stay up too late, though. Thanks. I haven't distributed them very accurately. Okay, and that's an exercise using those matrix methods we talked about yesterday. But it's got a twist in that there are 3 species involved, and so when you set up the matrix, you have a 3 by 3, and so it's you have 3 eigenvalues and a cubic equation to solve, which is never very nice. The way out of it is to recognize that one of the species, what I've called I2, reacts very rapidly, and so you can apply the steady state approximation to it and get its concentration in terms of the other 2 radicals, R and I1. And then you can set up, redefine the rate equations, and you then get a 2 by 2, and you can get eigenvalues lambda 1 and lambda 2. And it's a problem that we will use on Friday when we talk about autoignition. And in fact, I think we may even use it a little bit tomorrow as well. It's going to be useful to us later on. And it's a nice exercise on what we were talking about. Okay, so the next 2 topics relate to the determination of rate constants. And so first of all, we're going to look at experimental methods for determining rate constants. And then later on, probably later on today and tomorrow, we'll start looking at theory. Okay, so we're going to concentrate on reactions of atoms and radicals. We'll say something briefly about molecules later on in initiation steps. Slight caveat to that some some of the reactions that we'll be involved with are unimolecular reactions in which a molecule is falling apart to form radicals. We need to cover a temperature range from about 1,000 to 3,000 K for reactions involved in high temperature combustion, from about 600 to 1,000 K for autoignition, and about 200 to 300 K for reactions involving combustion-generated pollutants in the lower atmosphere, on the basis that we ought to be worried about those processes as well, since a lot of the problems derive from combustion-generated pollutants. So ideally, what we'd like to be able to do is to isolate the individual reaction and study it under the appropriate combustion conditions. That's the ideal. It's not always possible, and there may be other reactions occurring, and we may have to model the system in order to extract the rate constant that we need. And we may need to extrapolate to the appropriate temperature and pressure. So it's often quite hard using some of the techniques to measure at the high pressures needed. So we may have to extrapolate up to higher pressures. And sometimes we need to extrapolate to higher temperatures. And ideally, we would achieve this using theory. So we would either tune our theory to the available experiments and then use the theory to extrapolate. The techniques we're going to talk about are pulse laser photolysis, which is the technique that we use at Leeds, shock tubes, and you've got the world's leading exponent of shock tubes here in Professor Hansen, flow tubes for elementary reactions and for whole systems, and then static studies of whole systems. So we'll say a little bit about some quite old studies that generated an awful lot of important information. Okay, so pulse laser photolysis. So this is a typical experimental system. So we're going to need So this is the reaction cell here, and we flow, and we're going to look at OH reacting with SO2 in this case, and we flow an OH precursor, something that's going to allow us to generate OH, the reactant, and then some diluent, helium or nitrogen, through the cell. So it's a slow flow through the cell. It's not really a flow system, but we're flowing the stuff through the cell so that when stuff gets photolized, we sweep it out and start again. And then we have one laser here which photolizes this OH precursor. So this OH precursor could, for example, be hydrogen peroxide. So we take H2O2, we use a pulse of light, and we generate hydroxyl radicals. And that occurs in a time scale of the order of 10 nanoseconds. And then the most widely used technique uses what's called laser-induced fluorescence. And so we have a second laser here, which is a tunable laser. So we can tune it to any frequency within a certain range. And that light goes through the cell. And what it does is it's absorbed by OH. OH goes up to an excited electronic state. And then the OH falls back again, and it gives off fluorescence. So the OH fluoresces when it's been excited to this excited state. And once again, this is a pulsed laser, again, around about 10 nanoseconds. And so what we've got is we've got our cell. We've got one laser coming in, which is the photolysis laser. And then another laser, which is the dye laser, and that produces the excited OH, which then fluoresces. So light comes out from the OH, and we measure it with a photomultiplier. And what we have is a specific time delay, delta t, between this laser pulse producing the OH and this laser pulse monitoring the OH. And then we simply change that, we do the experiment again and change the delay time until we build up an overall picture. Okay, so we set the delay between the photolysis laser and the probe laser, and we repeat with many, many different delay times. And we generate a decay that looks something like this, and then we have to analyze that. Now, just let's think about that decay. What we've got is we're looking at DOH by dt, which is equal to minus the rate coefficient times OH times SO2 in this particular experiment. And we have conditions such that SO2 is very, very much larger than OH. And so even when all the OH has been removed, the SO2 concentration has hardly changed. And so we can replace this by minus K prime OH, where K prime is equal to the rate constant times SO2. And this is called a pseudo first order reaction. It's actually a second order reaction, but because one of the concentrations isn't changing, it behaves like a first order reaction. And so we can integrate that, and what we'll find is that OH is equal to OH0 times e to the minus K prime T. And there are two things to note from that equation. The first is that the OH is decaying exponentially. The second is that we don't need to know the absolute concentration of OH. We only need to know its relative concentration, because we can basically take this to the other side, and we're simply looking at the way in which OH decays relatively. Its concentration doesn't matter. And that's rather nice, because it's quite difficult to measure absolute concentrations using laser-induced fluorescence. So, but we only need the relative concentration. So the signal is proportional to the e to the minus kt. So this gives you a summary of what happens. So we have a short pulse of light, about 10 nanoseconds, into the reaction cell, which generates OH, which react with SO2. We monitor the OH as a function of time using laser-induced fluorescence. We only generate a signal that's proportional to OH, but that's okay if the reaction is pseudo-first order, as it is here. We do the experiment many, many times with different delay times and build up a decay. We can then plot log OH versus time, and the gradient is going to be minus K prime, which is equal to K minus K times SO2. So that we then repeat the experiment, the overall experiment, series of experiments many times, varying the SO2, plot K prime versus SO2, and the gradient is equal to the rate constant we want, K. And it's a tried and trusted method, and it can produce rate constants which are really quite accurate. So let's have a look at a couple of examples of that. So this is the reaction between OH and acetylene in the presence of a third body. So what happens is that OH adds to acetylene and forms this hydroxy species here, and so we need a third body to stabilize it, as we discussed yesterday. So So it's a pressure-dependent dissociation reaction. We study it as a function of temperature and of pressure. And so there's a typical decay. You can see the quality of the decay is very high. And this is that plot of the observed rate, first-order rate constant versus the concentration of C2H2. Again, very little scatter, so you can obtain the rate constant quite accurately from the slope of that. And then this is a whole series of temperatures going from 210 K up to 373 K as a function of pressure, as a function of the concentration of M. And you can see that the reaction is pressure dependent. The rate constant at high pressure increases with temperature, but the thing is also pressure dependent. This is an interesting example of a rather typical reaction between OH and, in this case, acetone. And these are really very, very carefully designed experiments. And what they do, this is a man called John Crowley. He, again, uses the same sort of thing, an excimer laser that dissociates an OH precursor. And then he has a dye laser that excites laser-induced fluorescence. And he uses the same sort of technique that I discussed in the last slide. He also uses a technique called resonance fluorescence, where he has a lamp that basically generates light of the right wavelengths to excite the OH. And again, he looks at the fluorescence. But this is not a pulse laser, this is a continuous lamp. And he gets another trace, which gives a lot of very accurate information. So this is an alternative method of monitoring the reaction. And then finally what he does is he recognizes that the concentration of acetone is reflected linearly in the rate constant that you're determining. So you need to measure that concentration quite accurately. Acetone is not the easiest thing to handle to high accuracy concentration, to make up a mixture to highly accurate concentration. So what he does is he measures the concentration of acetone in the mixture that's flowing into the cell using absorption spectroscopy, and then he also measures it coming out of the cell. They should be the same, because the acetone will not be consumed significantly, but there may be some losses on the walls. And so he would take the mean of those two measurements if they differed. And so he can determine those concentrations of acetone very, very accurately indeed. And here's the result going from temperature of 200 K up to 400 K. And the rate constant increases with temperature in the usual way at higher temperatures, but then it swings around at low temperatures, and it actually starts to increase as the temperature goes down. And some reactions show this even more vividly than this particular example here, and we'll discuss that later on. Okay, it's coming up to 3 o'clock. Any questions? Yeah. Okay, it's an indium YAG laser is a solid state laser that gives a short pulse of radiation about 10, 15 nanoseconds long. So, can't remember the exact wavelength, but it's about 1060 nanometers. So it's a very, very long wavelength laser. And so what you do is you double the frequency of the laser. So you convert it from 1060 to 503 nanometers. No, 530 nanometers is better, isn't it? Yeah. So to 530 nanometers, and then you use that to pump a dye laser. In fact, you'd not only do that, you'd probably go to a shorter wavelength still, to 265 nanometers. So this is what's called doubling, frequency doubling. And it's achieved in a crystal, a nonlinear crystal. And this radiation here is then used to pump a dye. So we have a dye, and we pump this dye, and we get a range of wavelengths out of it, but we select just one particular wavelength, which is the one that we want to use to excite the OH. So a YAG is a solid-state laser that's used to pump a dye laser. So there's nothing magical about it, but it's... Any more questions? Okay, would you like a break? Okay, we'll be back in 15 minutes.